the last part of this class, part E.3, 5-element partition. Yeah. So let's continue. All right. So before we start, let's look at let us do some analysis on our failed effort. In the previous video, we tried very, very hard, but at the end, we got failed. So we need to do some analysis. We try to improve it. So we try to, fine tune, try to, do some important, critical improvement and get a desired result. Yeah. So let's do that step first. Yeah. All right. So first, the 3-element based partition. So that's what we did in our previous effort. The reason why we choose 3-element based partition, because it's easy, right? Yeah. To organize all the elements in 3-element groups, then find the median of each group. That's easy, so easy. So we choose from a relatively easy way. So that's the main reason behind it. Yeah. And we expect, so our goal, the cost function our target should be big theta of n, not big theta of n log n. Okay? Yeah. N log n. Currently, we have n log n. Still, you can see one step away from the goal. But it is a significant step. Yeah. So we need to do some important improvement. Yeah. Yeah, but the method is pretty promising. Yeah. So if you look at the whole method, it is very smart. Okay? It gives us a result not quite there yet, but not too far away, right? Yeah, only a log n factor difference. Okay, yeah, reachable. Yeah, so we can treat, the distance is pretty reachable. Yeah. So we just make one last push, we can reach it. Yeah. So that's why we feel it is pretty promising, this method. Yeah. So that means although that method failed the previous time, we should not drop it. We should not throw it away. We want to keep it. Yeah. But we need to do some important adjustment. Yeah. All right. So we need to do this, tighten our estimate. How to tighten? There is some room to do it. Yeah, so there is room, because here, why you choose 3-element based partition? Although it's simple, but if it does not work, you should use a different partition, right? So that's the natural reasoning, different partition. Yeah. So as a conclusion, so based on this analysis, for our conclusion, we want to try the 5-element partition, 5-element based partition. Yep. It is a little harder, but we hope it can really tighten the estimate. Okay. All right, so let's do it. We organize the elements in 5-element groups. Yeah. Although we may have some extra elements, okay, certain number of extra elements, but that part is not really important. Remember, in our computer science, we allow some reasonable error. Yeah. If it's not too big, we can take it. Yeah. So that's why for our convenience, we just assume n this time is a multiple of 5. Yeah. After we get the result, finally we can easily make that small adjustment to take care of the 5r plus remainder term, any remainder term. So we can easily handle that part. Yeah. So then also that r, we want to still take r equals 2s plus 1, odd number, so that we can have a middle column that corresponds to the median of the median. Okay? Yeah, for convenience. Yeah. So no problem. We can do that assumption, make that assumption. Yeah. All right. Still, first step, this time find the median of each 5-element group. Okay? So that's another question in your homework assignment. The last question, question number 25. Yeah. It is pretty challenging. Yeah. Pretty challenging. Yeah. But I want you to try. So I give you some hint. Yeah. All right. The answer, 6 comparisons. In that step, we need 6 comparisons. We can find the median of 5-element array. All right? Yeah. So we will use that result. Yeah. All right. After that step, partition element. How to choose the partition element? M star, median of the median. Yeah. Median of the median through recursive function call. Okay? So we can get that. All right. So after that, we do the similar things. Yeah. So I hope you can remember part of the procedures we did. Yeah. Here, let me just do that part. Yeah. First, step 1, we want to find those elements that are guaranteed to be less than M star. Guaranteed. Okay? Yeah. So that step important. Yeah. So what are those elements guaranteed less than M star? First, these medians at the left-hand side of M star. Remember, when we define the function, the cost function, the recursive function, the cost function, when we return, remember the S array indices, we also return those indices that corresponds to the elements with rank numbers less than that of M star. Remember? Yeah. So that step is important in our assumption. Yeah. When we do that, we can have, all these elements are guaranteed to be smaller than M star. Other than that, how about all these elements? Because they are smaller than their corresponding median, but their corresponding median is less than the M star. So you can see all these elements are smaller, guaranteed smaller than the M star. How many of them? Yeah. All right. Yeah. Use these variables. Yeah. All right. Yeah. R. All right. Yeah. R rows. 2s plus 1. Yeah. Look at this. 2s plus 1. Total number of rows. 1 in the middle. So that one corresponds to the middle. That means the number of columns at the left-hand side of the middle column, S. Okay? Yeah. So S plus 1, S plus 1, but S, the third row, but we do not count M star, so we do not plus 1. So you can see 3S plus 2. The number of elements for block 1, 3S plus 2. Yeah. Similarly, part 2, those elements that are guaranteed to be greater than M star, this block, okay, also 3S plus 2. Yeah, so you can see that easily. All right. Then the third part, remaining elements that could be greater or less than M star. We don't know. All right. 2 corner blocks. Okay. 2 corner blocks. All right. 1 corner block here. 2S, right? Each row S. 2 rows, 2S. 1 corner block here. Also 2S. Okay? Yeah. Adding together, 4S. Okay? Yeah. So we have the 3 parts of the elements. With this information, we can do the partition. Do the partitioning. All right? Yeah. So next step, so let's do the partitioning. Yeah. Oh. Yeah. 5-element partition. So now we do it. We still draw the diagram to do it. Yeah. The array adjusted. C array different from the given original A array. Yeah. Because based on the median, we need to do some arrangement. Right? Median of the median. After we have the median of the median, we need to do some arrangements. So that's why we have the C array. Okay? All right. Then M star partition element must be in place. Otherwise, how can you use it as a partition element? You cannot. Yeah, in place. That means its rank is, is known. Yeah. Its rank is known. Yeah. Then we arrange the remaining elements at its left-hand side and its right-hand side. Yeah. We do that arrangement. Left-hand side, block 1, we can place them at the left-hand side of M star. Yeah. Easily. Block 2, we can place them at the right-hand side of M star easily. Yeah. Because the relationship, the elements in these 2 blocks with respect to M star are known. Okay? Yeah. Then for part 3, block 3, unknown part. But we do 4S comparisons. Each one by one, compare it with M star. Yeah. So after that 4S comparisons, we can determine part of these elements 3A less than M star. So we use number of elements A for it. Yeah. Part B, 3B, B, number of B elements greater than M star. Yeah. But these 2 numbers in this range. Okay? Yeah. So that's the partition step. All right. After that, we can derive the recursive inequality the same way as we did for 3-element partition. Yeah. So here, I do not need to go through step by step. I just give you the formula and explain a little bit. Yeah. All right. We want to estimate the cost function S of n. Then we use the worst case, so less than or equal to the cost of each step. Step 1, find all the medians of 5-element groups 6 times n over 5. Yeah, because n over 5, that's approximately the R number, right? Approximately R number. And each group, we need to use 6 comparisons. Okay? So that's our homework question number 25, right? Yeah. So we prepare for it. 6 times n over 5. So that's why 6n over 5. Second term, 4s comparisons. 4s, okay? And, so look at this here. And approximately equal to 10s. 4s, 4 out of 10. 4 over 10. That's why 2/5 of 10, of n. 2/5 times n. So the second term. Yeah. The third term, median of median. The size, the number of medians, r is n over 5. Okay? So that's that step. The cost is s of n over 5. Recursive call. Yeah. Then elimination, the last step. We drop either block 1 or block 2, because that part, one of the 2 blocks can be can be eliminated 100% sure. One of the 2 blocks, either smaller, the elements in that group are smaller than m star, or the elements in that group greater than m star. One of the 2 can be dropped, eliminated. But for the worst case, what's the size of the worst case? The part you drop it, 3 over 10, 7 over 10, right? The remaining 7 over 10, 7n over 10. Yeah, so that's the worst case, remaining problem size, 7n over 10. Okay, all right. So that is our recursive inequality. Yeah. A little harder, yeah. And in this method, a little harder. Yeah. I hope you can follow the details. Yeah. Initial condition, that's easy. Yeah. So we simplify the recursive inequality. So the last step, we need to solve it. And when we solve it, this time, we need to use the recursion tree. Okay? Yeah, we need to use that recursion tree. Yeah. Just as we did for 3-element partition. Yeah. So the last step. Let's work on it. The tree. Yeah. The root node S of n split into 2 branches, right? Corresponds to each of the 2 subproblems. Yeah. Left-hand side subproblem, right-hand side subproblem. Okay? Yeah. Non-recursion cost. Non-recursion cost for the root level 8n over 5. Okay? Then let's move down. At each node, when we do the split, we need to pay certain non-recursion cost. But how do you calculate the non-recursion cost? That's easy. From here, that is 8/5 times the size number. Here, what is the size number? N over 5. So 8/5 times the size number, n over 5. So that is the 8n over 25. Yeah. Similarly, the right subtree, we can do the same thing. Yeah. After that, we want to combine all the non-recursion cost in this level. Okay? Same level. Yeah. After that combination, 36n over 25. Yeah. But we want to compare with the previous non-recursion cost. We want to look at what is the relationship. Yeah. So we can write it as 9/10 times the previous recursion cost. Here you can see the non-recursion cost in the next level is reduced comparing with the previous level. So each level, the non-recursion cost is reduced. You can see this phenomenon is different from our 3-element partition. For our 3-element partition, the non-recursion cost is not reduced. At every level, it keeps the same. Same non-recursion cost number. And here, it is reduced. That's the significant difference. So that's really the property we need to solve this problem. All right, so let's keep going. Yeah. The number of levels still log n. Yeah. So using the same way we did as in the 3-element partition. Okay, so n over 5 to the kth should be approximately equal to 1. So then, n approximately equal to 5 to the kth, and the k approximately log base 5 of n. Okay, log base 5, this time log base 5, but we don't worry about the base number. Okay, yeah, just some constant. Yeah. All right. And here, another interesting thing is, this number of level, this number is not important for this current method. Not important anymore. Why? Because there is another much stronger factor that dominates this one. There is another factor. That factor, its impact is much bigger than this one. So that one dominates this one. So this one becomes not important. How is that? So let's see our estimation formula. You will see it easily, yeah, in the formula. All right. Now, let us collect all the non-recursion cost of all the levels. Yeah. Each level, remember, we multiply the common ratio, 9/10 common ratio, right? Every term, we multiply that common ratio. Yeah. So we get a geometric series. Is this a geometric series? Geometric series. Okay? Recall from your discrete math, geometric series, but it is an infinite geometric series. Okay? Yeah. We can even, we are very generous. We know the number of levels cannot be infinity, right? Cannot be infinity. But we are very generous. We can handle the even infinite number of terms. We can handle it easily. So that's why we don't worry about the number of levels. It is not important anymore in this formula. See, how many terms here? Not important anymore. Okay? Yeah. Even infinite number of terms, we can estimate easily with the formula. Okay? So using the formula for the infinite geometric series. All right. The first term, 1 over 1 minus the common ratio. Common ratio. Okay? All right? Yeah. So that's the formula. Yeah. After simplification, we get 16 times n. 16 is a constant. Okay? Yeah. After that, look, is that what we need, our goal, matching our goal? Big theta of n. The constant is not important here. 16, 100, that constant is not important here. So you can see with the tightening, changing from 5-element method to, 3-element method to 5-element method, we make our estimation tighter and finally reach the goal. Remember the reachable, right? Yeah, so as we describe it, that log n, not quite there yet, but reachable. Yeah, just another step of improvement. Finally, we get there. All right, so after this whole solution from part D, part E combined to halves, our conclusion. We can solve the general selection problem in linear time. That is our final solution. Okay? We can solve the general selection problem. How well you can solve it in linear time. That is our final solution. Okay? So after this, selection problem has been solved completely. Okay? Although the detail not that easy, you need to pay a lot of effort to understand. But if you follow all the details, you will feel comfortable with the solution. Okay? All right, so let me just finish the whole part E at this point.